we are trying to make our way toward a definition of transcendental functions in the complex plane. Things that are not merely powers of z, but which might allow us to take the sines and cosines of complex numbers, take the logarithms of complex numbers, take exponentials of complex numbers. What would it mean to raise a number to a complex exponent, right? Questions like that. How do we take what we know about the arithmetic of the complex plane and get there? Well, it's kind of a long process, and in our previous video, we made an important step forward. What we figured out was that the polar form of a complex number behaves an awful lot as though the modulus, the distance of that complex number from the origin, is a coefficient in front of an exponential expression, a power, right, where the base of that power is being raised to the theta, the argument of that complex number. And the reason that this is a good guess is that exponentials multiply together in the way that we would expect complex numbers to multiply together, given the calculations that we did from the last video. So our hope is that we're able to write any complex number as its modulus times something raised to the power of its argument. So then the question is, what is that something? What is this common base that's going to allow us to, on the nose, represent every complex number as modulus times that base raised to the power of the argument? That's what this video is, and the discovery in this video is one of the key moments in the development of the theory of complex numbers. So let's get there. So in complex numbers, we observed that when they multiply, the moduli multiply and the arguments add. And that is what led us to this motivated idea that we may be able to write any complex number, which in its modulus argument form is r cosine theta plus I times r sine theta. We should be able to write that as r times some base raised to the power theta. We need to figure out what that base is. Well, in order to investigate this equation further, let's assume for the moment that we do not have a modulus equal to 0, so we're looking at a non-zero complex number. If I were looking at the complex number 0, then the modulus would be equal to 0, and the argument would actually be undefined. We can't measure what is the angle that the 0 vector makes with the positive x-axis, right? It could be any angle we choose. So we're going to rule out the 0 case and think of just a non-zero complex number, so that what that's going to allow us to do with this equation is divide out the r's. Anytime I divide by something on both sides of an equation, I had better be pretty sure that that thing I'm dividing by is not 0. A lot of high school students get wrapped around the axle on that when they're doing algebra. But if we take the assumption that r is non-zero, now we can focus in on just the theta portion, just the argument portion of this expression. So our question is, what base b is going to make it so that b to the power theta is the same as the cosine of theta plus I times the sine of theta? So I don't know what's going on the right-hand side here yet. That's kind of the point of this video, is to figure out what b is. But I do know some stuff about the left-hand side. I do know how the cosine and the sine of an angle can be expressed in a different fashion. And that different fashion is going to come from our second semester calculus course. So this is the first time where we're going to reach into calculus in our study of the complex plane. And the tool that's going to help us get there is the Maclaurin series. The Maclaurin series of a function, a differential, actually a smooth analytic function in calculus, is a way of expressing that function as like an infinitely long, infinite degree polynomial function in the argument, which in this case is theta. And you spend a lot of time in second semester calculus figuring out how infinite series of functions work, where the series are all built out of powers of the variable. Where do they converge? Where do they not converge? And how do we relate them to transcendental functions? And so what that looks like in practice, in the case of cosine theta and sine theta, so the cosine and sine functions, remember theta here is a real number, right? So we're not doing anything fancy. We're not doing anything in this expression here that we couldn't have done in real variable calculus. And in real variable calculus, we can express the cosine of theta as an infinite series in the variable theta. If we do that, we can determine the coefficients of this series, 1 and then 0, so there's no theta to the first power term, and then the next coefficient is minus 1 over 2 factorial, in other words, negative 1/2 times theta to the power 2. Theta to the power 3 does not appear. Theta to the power 4 has a coefficient of positive 1 over 4 factorial, and so on and so forth. When you study Calc 2, you figure out that these coefficients that come in front of the powers of the variable can actually be determined by the derivatives of my function evaluated at a certain point. And in this case, that certain point is theta equals 0. That's what makes this a Maclaurin series instead of the more general idea of a Taylor series, which can be expanded around any point, not necessarily 0. So this identity, sort of a classically known identity, and it's one that in second semester calculus we end up unveiling. So that's how I can write the cosine of theta in terms of powers of theta. And this pattern continues off to infinity, right? The more terms I include, the closer that this polynomial on the right-hand side becomes to the cosine of theta. It actually has an infinite radius of convergence. At least when we study it in calculus 2, it does. So any theta that I want, I can plug into the right-hand side, and it's going to converge to the cosine of theta on the left-hand side. So that's what the cosine of theta looks like expanded into a series. Sine of theta, well, before I do the sine of theta series, I want to not be ignorant of this I that's sitting in front of it. So I'm going to make sure that every term that I write here for the series for sine of theta is also multiplied by an I, just so we don't forget the I that's sitting there. It's going to be really important in what we're about to do. So what is the sine of theta in a Maclaurin series from calculus 2? Well, since sine ends up being an odd function where cosine was even, as an even function, you'll notice that all the powers of theta that appeared in cosine's Maclaurin series all have even exponents, theta to the 0, theta to the 2, theta to the 4, whereas the sine of theta is an odd function. And so we only get the odd powers of theta happening here. So sine of theta is theta minus 1 over 3 factorial theta to the third power plus 1 over 5 factorial theta to the fifth power, and so on and so on. So what we're trying to do is we're trying to take those two series that are written on these two lines here and somehow smush them together. Right? And if we can smush them together in just the right way, we may be able to discover what the value of b is on the left-hand side, such that the series expansion for b to the power theta should exactly give us the sum of what we're seeing on these two rows. Well, one of the biggest obstacles to figuring out how to smush these two rows together are the presence of these alternating signs. Both cosine theta and sine theta give us these alternating coefficients, right? The first term has a positive coefficient, the second term has a negative coefficient, the third term has a positive, and so on and so forth. That happens for both the cosine of theta and for the sine of theta Maclaurin series. So how might we be able to take those minus signs that exist in this expression and flip them all to pluses without screwing up the pluses that we have elsewhere in these two series? In other words, how can I just make it so all my coefficients are positive instead of then being alternatingly positive and negative, because that's going to make it more challenging for us to see what's going on. And the key here is to realize that there is another set of things which also alternate in sign. So 1 followed by -1 followed by 1 followed by -1. I can express those as powers of the complex number I. 1 is the 0th power of I, but -1 is the 2nd power of I. Positive 1 is then again the 4th power of I, -1 is the 6th power of I, and so on and so forth. So every -1, if I see a -1 somewhere in this sum, I could replace it with I squared. If I see a 1, and if it fits my purposes, I could replace it with I to the 4th, and so forth. So any 1 or -1 that I find, I now have a power of I that I can replace it by. And this accounts for the even powers of I. What about the odd ones? Well, I to the first power is I to the third power is minus I to the fifth power is I again, and so forth. So that means anywhere I see an I, if it suits my purposes, I can replace it with either I to the first power, or I could replace it with I to the fifth power. If I see a minus I could replace it by I to the third power. So this gives us a way of taking ones, minus ones, I's, and minus I's, and replacing them all with a suitable power of the imaginary unit I. And we're going to use that to our advantage to rewrite what we see in this sum of two series. So this -1 that I see next to the theta squared, it's probably a good idea if I can write it as a square of something. And lo and behold, -1 is just another name for I squared. So I'm going to replace this -1 that's sitting right here with plus I squared instead. Convince yourself before you, so pause the video and convince yourself that we didn't do anything illegal here. And now that you've unpaused the video, let's keep going. If I keep going, I could take this +1 over here because it's sitting next to theta to the power 4. It would be great if I could replace it with something that's raised to the 4th power. And sure enough, +1 is just another name for the 4th power of the imaginary unit. So instead of writing it as +1 over 4 factorial, I'm going to write it as plus I to the 4th over 4 factorial. Again, pause the video and make sure that I haven't done something illegal here. And now that we're back, that's what we would then continue doing for all of the even powers of theta that appear in the Maclaurin series for cosine of theta. What we're going to end up with is we're just going to end up with the corresponding powers of I being parts of these coefficients. And what's great about that is that the power that I is being raised to matches the power that theta is being raised to each and every time. That's important. Let's do the same thing for the series for sine theta. So this I here is already I to the first power, and it's already stuck to the theta to the first power. So that looks pretty good. So let's go to the third power term over here, where I have a minus I. And I would love to rewrite that as something to a third power, because it's going to be multiplying theta to the third power. And sure enough, minus I can be rewritten as plus I to the third power. Convince yourself that that is not illegal, and we'll move forward to the fifth power. We have 5 powers of theta here, so it would be great if I could rewrite this using a fifth power as well. And I is the same as the fifth power of I. So I'll write that as plus I to the fifth. When I go through and I make all of these substitutions, I have completely wiped out all the minus signs that we used to have in our combination of 2 Maclaurin series. And why that's great is that now it's easier for me to add these series together and have all of my terms have positive coefficients. So my constant term comes from this 1. My linear term comes from I times theta. My quadratic term is going to be this one, I squared over 2 factorial times theta squared. My cubic term is going to come from here. My fourth power term is going to come from there. My fifth power term is going to come from there, and so on and so on. And the other thing that we notice, and the reason that we wanted the power of I to match the power of theta, is that we can use properties of exponents to then factor out that power. And we get a series in terms, not just of theta, but in terms of the variable I times theta. Right? We get I theta squared from here. We get I theta quantity cubed from there. I theta quantity to the fourth from there, and so on, and so on. And then we look at the coefficients of that series. 1 followed by 1 over 1 factorial, followed by 1 over 2 factorial, followed by 1 over 3 factorial, followed by 1 over 4 factorial. And we say to ourselves, where have we seen that before? And this is another thing that we often do in calculus too. It's not just about taking a transcendental function and determining a Taylor series for it. It's also looking at a series and, when possible, figuring out what better known, more simply expressed function that series might add up to, might converge to, wherever it converges. And this looks an awful lot like the series 1 plus x squared over 2 factorial plus x squared over 3 factorial, and so on and so forth, which is one of the most recognizable Taylor series that students learn in second semester calculus. And it is the series for the exponential function e to the x. That thing that just happened right here, that is the big deal of this video. It's taken us only 12 minutes and 45 seconds to get there. I promised only a couple more minutes left, and we're going to button this all up. But this is the key insight, that when I add these series together, now that I have rewritten all of the coefficients to have powers of I in them so that we can get a series whose variable is I theta, that series which I get is exactly the series for the exponential function e to the x, where e is Euler's number, 2.71828122846 ... This number that, again, is one of those numbers that you learn in your 10th and 11th grade curriculum, usually Algebra 2. Students see that number for the first time, or at least really get intimately acquainted with it. And so if 1 plus x squared over 2 factorial and so forth, if that adds up to e to the x, then what does our expression add up to? Well, the role of x here is being played by I theta. So our series adds up to e to the power I theta. And we have finally arrived at a way to represent e to the I theta as being what we mean by cosine of theta plus I sine theta. In other words, this mystery base that we have been hunting for this entire video is actually e to the power I, somehow. That's kind of interesting. This fact that the polar form of a complex number can be expressed as an exponential expression is often known as Euler's identity, or Euler's formula. This was such a fundamental discovery that when it came along, it sort of revolutionized how mathematicians and scientists thought about complex numbers, because it explains so many more of the phenomena that we see complex numbers do when we apply arithmetic to them. So what this all means is that any non-zero complex number, z, if its real part is x, its imaginary part is y, I can write that again as r cosine theta plus I times r sine theta, but that number z can be written as r times e to the I theta, where the role of r here is played by the modulus of my complex number, the square root of x squared plus y squared. It's Euclidean distance to the origin in the complex plane. And the role of theta is being played by the argument, the angle that that complex number makes with the positive real axis. And of course, z being 0 just means that we would take r to be 0, and we could take theta to be anything we want. Right? But as long as z is non-zero, the principal argument, the theta, is well defined between minus pi and pi. So this is the key insight. This is going to be how we discover, for example, what it means to raise a number to an imaginary, or indeed a complex, power. What does it mean to like multiply 5 by itself I numbers of times? Like what would 5 to the power I actually be? Now that we have this identity in our hands, we can answer wacky questions like that. And now that we understand how imaginary powers work, we can also develop a theory of what is the exponential function as a complex function. What is e to the z like as a transformation of the complex plane? You can see how this identity that we worked so hard in this video to discover really unlocks a whole new world of complex functions for us to study as transformations. And Euler's identity, e to the I theta is cosine theta plus I sine theta, that is the identity that powers the whole thing.